Welcome to another video. Today we're going to be talking about a concept known as the Laplace transform. The Laplace transform is useful for transforming differential equations into algebraic equations, and you can probably imagine why this would be a useful thing to do, since the analysis of differential equations can become pretty complicated. So to begin, the Laplace transform is essentially a machine, right? So it's going to take some function in the variable t, which stands for time, and it's going to convert it or transform it into a function of s in what's known as the frequency domain. The notation will be this fancy L and then curly brackets that brace the function in terms of t. So here we have the time domain, the function in the time domain. And then once we apply this Laplace operator, we end up in the frequency domain. All right, so if we were to write this analytically, we could actually say that the Laplace transform of the function in the time domain is equal to the function in the frequency domain, and that is given by this expression here. It is a unilateral infinite integral with a product of two functions in the integrand. No big deal. And so the best way to do this is to just start with some examples. And so I'm going to start. One thing worth mentioning before we do examples too is the linearity of the Laplace transform. And that is to just say that it is a linear operation, meaning that the Laplace transform of a constant times a function is just that constant times the Laplace transform of that function. Similarly, the Laplace transform of the sum of two functions is the sum of the Laplace transform of the two functions. This is linearity. And so then it follows that, if you had something like this, you have this linear combination where you can factor out the constants and make two terms instead of just one. Okay, so that demonstrates the linearity of the Laplace transform. Now let's just do some examples. Find the Laplace transform of the following functions. We'll start very simple with the constant function. So we're just going to go through the common algebraic functions, and we're going to take the Laplace transform of some of them just to get the idea, to get used to using the formula, developing intuition, things of that nature. So let's say f of t is just a constant. We'll say 6, right? That means that the Laplace transform, or the function capital F in the S domain, is equivalent to this unilateral infinite integral of the product of these two functions. Rewriting this, we can see that and integrating, we end up getting negative 6 divided by s e to the negative st. And this is evaluated from 0 to infinity. Let's just do that right now. What is this function right here when t is evaluated at positive infinity? That's going to give us 0, right? So we have this negative 6s out here, and then we're going to have the difference inside. Let's subtract what happens when t equals 0. This turns out to be 1, right? So in these parentheses, we have 0 minus 1, and that's going to end up giving us 6 over s. And so therefore, the Laplace transform of the function f of t equals 6 is 6 over s. Try another one. Let's say f of t is equal to 3t, right? So then we'll just say that the Laplace transform, we're going to apply this integral. Probably many of you recognize this as integration by parts. I find the best way to do this is to use the tabular method. Write this a little cleaner. Yes. And so what I'm doing is I'm just taking derivatives of each of the two functions separately, and then we're going to do diagonal multiplication with alternating signs. So if I do that, I just end up we're going to go, let me write this on the other side here, so plus, minus, and we're going to go this way. Yep. So we just get 3t times negative 1 over s e to the negative st. And then we get minus 3 times 1 over s squared e to the negative st. And then any other ones are just going to be equal to 0, because the derivative of 0 is then going to forever be 0. So you'll have that factor of 0. So we're done with the integration here. But now I have to evaluate it at the bounds. Now what's going to make this easier is if I kind of manipulate this a little bit here. So I'm going to switch the place of the 3t and the 1 over s, and then the 3 and the 1 over s squared. And so now if I evaluate these at the 0 to infinity, what happens at infinity when t is infinity? Well, this term goes to 0. Anything times 0 is 0. So we have a 0 and then minus what happens when t is 0. You get a 0 here. You'll get a 1 here, but 0 times 1 is 0. So we have 0 for this term. Now, what happens over here? It looks like we have t to the, or e to the negative infinity is going to be equal to 0. But then we subtract the 0 portion. So what happens when t is 0 here? Well, this goes to 1, and this is 3, and this turns into 3 over s squared. And so it looks like the Laplace transform for this function 3t equals 3 over s squared. All right, so let's do for t to the n. Let's see what happens there. So this is a really cool one, actually. So let's say f of t equals t to the n. And basically we can, let's just see what happens if we just go through with this here. I'll keep it in pink so that we know that we're kind of just testing something. I'm just going to plug this directly into the formula. All right, let's start doing our integration by parts. Looks like this is going to go on forever if I write it like this, huh? And so I'm going to stop writing it. And I'm just going to think, okay, well, what can I do here? Because I don't want to be stuck here writing this for eternity. I'm going to test a value. I'm going to say, let's let just n equal 3. Okay, so if we do that, then we're going to get put this in white. And so taking the successive derivatives, and doing the cross multiplication here, and alternating the signs, right? We end up getting that this integral is equal to t cubed times negative 1 over s e to the negative st minus 3t squared, and then times the quantity 1 over s squared e to the negative st. plus 6t times negative 1 over s cubed e to the negative st minus 6 times 1 over s to the fourth e to the negative st. It's kind of lengthy algebra here. I'm going to do the same thing I did in that previous problem. I'm going to switch the positions of the factors in t and the factors in s. So here we're going to have negative 1 over s times t cubed e to the negative st minus 1 over s squared times 3t e negative st minus 1 over s cubed 6t e to the negative st minus 1 over s to the fourth times 6e to the negative st, all evaluated from 0 to infinity. I'm going to do some more quick algebraic manipulation here on this. You can check this. I'm just going to write it down so that it's here, but this is going to equal 1 divided by s times t cubed plus 3t squared over s plus 6t over s squared plus 6 over s cubed for t equals 0. And think about why I made that simplification. Like, why did I do that step? I'm going to finish this out here for t equals 0, and we're going to end up getting that this equals 6 over s to the fourth power. And what is 6? Well, so 6 is 3 factorial. And I want you to keep this in mind because in the next video we're going to talk about this. And this is s to the fourth. Repeat this exercise for f of t equals t to the fourth. And then, so pause the video, repeat the exercise for t to the fourth, notice something, but I'm just going to write it out here. You should observe that, in fact, that the Fourier transform of the function t to the n is equal to n factorial divided by s to the n plus 1. Okay, so this is the result you should get. And really, if you know that this is happening, then t to the n, you can really just say then that t to the fourth, which if you calculate it with that long integral, it's going to take you a lot of time. And when you can just use these formulas, which there actually is a table of values, and we're going to use that extensively. But here n equals what? N equals 4. So let's just take the factorial of 4. And then what's n plus 1? Well, it's 4 plus 1. Simplifying this, we end up getting 24 divided by s to the fifth power is the Fourier transform of t to the 4. All right. The next example, and we'll move quickly here. This one isn't too bad, but it is fundamental. we're going to say find the Laplace transform of f of t when it equals e to the at. Okay, so typically we just start out with our formula here. This unilateral integral and so I'm going to do something clever here. I'm going to notice that the multiplication of the same bases here raised to the exponents, remember we can just add the exponents in this case and make it like 1. And so when I do that, I'm just going to say that this equals t times a minus s, and you'll see why in a second. It's actually because this is how the integral will converge as the values of t go to positive infinity. And so by doing that, I have one exponential function All right, what's the integral of e to the t times a minus s? A and s are constants. Constants. So we know how to do this. Okay, and then e to the t times a minus s evaluated from 0 to infinity. Let's recast this in a different way. Let's say this equals 1 over a minus s times e to the at, e to the negative t s, 0 to infinity. All right, so here comes the fun part. E to the at as t goes to infinity, that's going to be infinity, but then we're multiplying it by e to the negative t, which is infinity, which makes this 0. All right, now we repeat the procedure for the 0. So e to the 0 is 1, e to the e to the 0 is 1. So we have 1 times 1. This whole thing just equals -1, and because we negated it, we can actually just reverse the order of this difference. That's a really quick way that we can negate rational terms. And so that equals 1 minus s over a. That is the Fourier transform of the function e to the at, where a is any constant. Okay, and then let's try to find the Laplace transform. Those are supposed to be curly brackets. Okay, so now we're going to do e to the negative at. Let's see what happens with that, right? So you've probably got the hang of this. Pause the video and practice if you would like. But this one is basically the same as the last one. It's just we get a slightly different result. So negative at, that's the difference. Notice how we don't have a difference in the denominator anymore. And we have a negative t here, which is good for infinite integrals, right? It guarantees that they're going to converge. So negative 1 over s plus a times, what are we doing here? So e to the negative infinity minus e to the 0, a situation we have encountered before. This thing just goes to what? 0 minus 1, that just equals negative 1. Get rid of that because of that. And positive 1 over s plus a is the Fourier transform of the function e to the negative at. Okay. I think that this was a good introduction. Next time we're going to introduce a table of values, perhaps derive a little bit more of the common functions, but essentially this is the gist of it right here. This is the Laplace transform, and we'll work on in the future applying this to differential equations and simplifying them into algebraic ones. So I hope this helped. If there's anything that you would like me to clarify, please leave it in the comments. Also, if there's anything that you would like me to cover in the future, I would be happy to oblige. Thank you for watching and have a wonderful evening.